Okay, in this video, we're going to continue our study of dynamics, but we're now going to be adding in friction. And we're not really adding in friction. We've been dealing with friction before, but previously I've always given you guys friction and just told you what the number is. So for example, I'll say there's some force of friction equal to some number of newtons opposing motion, right? We're now going to take a closer look at friction, uh, where it sort of comes from and how we can calculate the friction in different situations, okay? So when we're thinking about friction, we want to be thinking about a force that opposes relative motion between systems in contact. Okay, so friction is going to be a force that's always opposing the motion that's happening in these problems, right? So we're going to have two systems that are in relative motion. They're going to be in contact, and friction is going to be opposing that motion. And I should note here that everything that we're going to be talking about here corresponds to Chapter 5 in your text. So we're moving on to Chapter 5 now. Okay, so friction for our purposes is going to come in two flavors. We're going to have kinetic friction and static friction. And what are those and what are the difference between the two? Okay, so kinetic friction, which we're going to symbolize as F with this sub k, so it's a lowercase f with this subscript k. This is going to stand for kinetic friction. Kinetic friction is the force of friction that opposes the motion of two objects that are in contact, and these objects are in relative motion to one another, right? So we have two objects which are in contact, let's say a box and the ground, but kinetic friction comes into play when the box is already in motion. Okay, so kinetic friction is the friction that's going to oppose that motion when the object is already moving, when the two objects are in relative motion to one another. Static friction, which we signify with this F with a subscript S, is going to be the force of friction that opposes motion when these two objects are stationary relative to each other. So, well, we're going to take a look at an example in a second, but keeping with our box example, this is similar to having a box sitting on the ground, and how much force do you need to apply to this thing before it starts moving? Well, the static friction is going to be what tells us how much force we need to apply to this box before it starts to slide. Okay, so note that well, we have our expressions here, right? We have our expression for our force of kinetic friction and for our force of static friction. And note that both of these expressions depend on the normal force, N. That's what our N here signifies. And that's kind of intuitive, right? We would expect that there would be more friction if an object is heavier, right? So if there's more force jamming the object into the ground, and the ground has to exert more force to keep this thing from accelerating into it, then there's going to be more friction, right? And it's going to be harder to push this object along. Also, the symbol that you see here, this Greek letter mu, it kind of looks like this, kind of like an M almost. So the Greek letter mu is what we're going to use to signify our, oh no, it closed again. It's going to be what we use to signify our constant of friction here. Let me just reopen this thing before I get back into this. Okay. Right, so sorry about that. Right, so where was I? We were talking about the normal force and then mu k and mu s. Okay, so these are just our coefficients of friction. So coefficient of kinetic friction or coefficient of static friction, depending on which type of friction we're talking about. And these are just numbers. These are numbers that we can look up in a table, and they're going to depend on the types of materials that are in contact, right? So, for example, if we had a wooden box on a cement floor, there's going to be some coefficient of kinetic and static friction that we need to look up from a table, and you can look up that information from table 5.1 in your text. So we need those numbers to be able to do these calculations, right? These are values that would have been that we would get experimentally. So we would do a number of experiments and calculate what these constants would be, and they're all tabulated on table 5.1. So as I was saying, for example, wood on concrete would have one set of coefficients of friction, where whatever ice on steel would have another one, and so forth, right? So we need to look these up to be able to do these calculations. So let's take a look really quickly and a sort of thought experiment that we can do here, a problem that's going to involve both of these types of friction, right? So let's consider a box on a concrete floor again. If we start to apply a force, some force F to the box parallel to the floor, so we have the box sitting on the floor, we're pushing on the box from the side, right? And maybe I can, I didn't really leave myself any space here to draw this out, but I'll kind of draw it really close here in the margin. So we can imagine a box on the floor, right? And we're applying some force F to it, right? And so, so in the beginning, as we crank up this force slowly, the box is not going to be moving, right? Like when we just start to push the box, it's not going to start moving because the force of static friction is greater than this force that we're applying, right? Than the magnitude of the force that we're applying. But as we push harder and harder and we crank this F up, eventually our capital F, the force that we're applying, its magnitude is going to be greater than the force of static friction opposing our motion, right? So there's going to be some force of static friction opposing our motion here. And so as F, capital F, becomes larger than F sub S, this thing is going to start to move, right? But the second this thing starts moving, F sub S is no longer something that we need to consider. It's no longer opposing our motion because we're now in motion, right? It's the force of static friction only applies when the two objects are stationary. The ground and the box are stationary in relation to one another. So when the thing starts moving, then what's opposing our motion? Well, then the force of kinetic friction is opposing our motion, right? And we have to look up what that coefficient would give us, and then we know what our acceleration will be, right? And we're going to look at a few problems with this in a second here. Just a couple of quick notes before we do move on to the problems, and I'll probably erase this little scribble here. A couple of quick notes before we move on. The first note is that the force of static friction is always going to be greater or potentially equal to the force of kinetic friction, right? So what this is telling us is that it's always more difficult to get an object moving than it is to keep it moving. Okay, so as soon as we get the object moving, because we've applied some force large enough that it's going to be greater than the force of static friction, if that force continues to be applied to the object, it's going to start to accelerate, right? And it's going to continue to accelerate because we know that the force of static friction for any normal system that we're going to run into is going to be greater than the force of kinetic friction. Okay? The second thing to remember is that friction, whether it's static or kinetic, always opposes motion parallel to the surface. And it can never cause motion, right? So no matter how much friction you could have a very large static friction keeping your objects stationary relative to one another. But no matter how large that force of static friction is, it's never going to cause any motion. It'll always just oppose the motion that's being caused by other forces, right? And finally, our friction is always going to be perpendicular to the normal force. And because our friction depends on the normal force, and we're going to look at that in the next two problems here, it kind of becomes sort of clear why that has to be, okay? So let's take a look at a couple of examples here. So this is the first, maybe the simplest example that we can look at. So assume we want to push a crate on flat ground. We know that the materials that make up the crate and the ground interface such that our coefficient of static friction is going to be 0.45 and our coefficient of kinetic friction is going to be 0.3. Okay, so first, before we get any further into the problem, a couple of interesting or important things to notice here. We know that our force of static friction is always going to be greater than or equal to our force of kinetic friction. And because our force of static friction is just going to be equal to our coefficient of static friction times the normal force, and our force of kinetic friction is going to be our coefficient of kinetic friction times the normal force, then it stands to reason that our coefficient of static friction is always going to be larger than or equal to our coefficient of kinetic friction. And that's true here too, right? So we have 0.45 and 0.3. So that's good. That's what we would have expected. Okay, second thing. And what was the second thing that I wanted to note here? Right, that there are no units on these, right? So these coefficients, mu sub s and mu sub k, these are coefficients of friction, and they don't have any units. They're just numbers, okay? So don't worry about units for these. They should have no units, okay? So let's continue with the problem here. We also know the mass of the crate is 100 kilograms. We now want to find F sub s, so our force of static friction, and F sub k, our force of kinetic friction, so that we know how hard we would need to push on this crate to get it moving, right? To get it moving and to get it accelerating once it is moving, okay? And so let's take a look at this. The first thing that we always want to do is draw ourselves a diagram. So let's start off with that. Let's say we have our crate here, and we have our floor. They should be in contact, but we know what's going on here, and so we can imagine that we're applying some sort of a force here. We have the force of gravity pulling down on this thing, right? And we have some normal force keeping this so that it's not accelerating into the ground. And then we're going to have, well, let's assume that we're pushing to the right here, so we're always going to have some friction opposing this motion. Now, I'm just going to leave it F without a sub s or sub k, because this could either be F sub s if it's static before it starts moving, or once it starts moving, we could represent that with an F sub k. So it can be s or k, and we'll worry about that afterward. And I'm just going to put some coordinates in here. Let's call this x and call that y. Okay, so what are we interested in? Keep our eye on the prize here. All we really want is the force of static and kinetic friction, right? So let's see how we could calculate that. Well, we know from these two equations up here that what we need to get at is the normal force. As soon as we can get at the normal force, we right away can pull out F sub s and F sub k just by hitting it with our coefficients of friction, right? So what is the normal force? Well, let's start off by looking at the problem vertically. So vertically, what does Newton's second law tell us? Well, Newton's second law tells us that F net in the y direction needs to be equal to the mass times the acceleration in the y direction. And we know from several other previous problems that the acceleration in the y direction, and I mean clearly, because this thing isn't lifting off or going into the ground, that has to be 0, so this is equal to 0. But the net force in the y direction is also equal to n minus mg. But since n minus mg is equal to 0, well, that means that n is equal to mg, right? And that's our normal force, right? So since we have an expression for our normal force, we can very easily just substitute this back in to the two equations we have up here, and this is going to give us the following. F sub s, our force of static friction, is simply going to be mu sub s times n, and that's just going to be 0.45 times, well, mg from down here. Well, m is just 100 kilograms, and g is just 9.8. If we do the math here, we're going to find that F sub s is just, 441 newtons. And if we do the same thing for our force of kinetic friction, except now with mu sub k, we're going to find, and I'll just write it out here, we're going to find that the force of kinetic friction opposing motion is going to be equal to 294 newtons. And again, it's smaller than the force of static friction, and that's what we would expect, right? So we now know how much force we would need to apply to first get this thing moving, and then we could tell how much surplus force. Let's say we got this thing moving with 450 newtons. Well, then we would know once it's moving what the magnitude of the force of kinetic friction opposing that motion would be, and from that we could calculate accelerations and so forth. But we're not going to do that in this problem. Okay. Let's take a look at a second example, and that'll be the last example for this video. And we'll move on to other stuff, well, other examples in the next video. Okay, so in this one, we're looking at a 62 kilogram skier sliding down a 25-degree slope, and we want to find what the coefficient of kinetic friction, our mu sub k, is if our force of kinetic friction is 45 newtons. Okay, so let's start off again by drawing the problem. So we would have our slope here. This would be theta, and theta is going to be 25 degrees. This will be our skier. of mass m. We're told m equals 62 kilograms. And let's draw some forces on here. Well, first I'm going to draw some coordinates, and similar to the way that we dealt with the previous problem on a slope like this, we're going to want to break all this stuff up into either parallel or perpendicular to the surface. And if you don't remember this sort of type of problem, I would definitely recommend you go take a look at a couple of the previous videos where we talk about this sort of problem. That theme of breaking it up into parallel and perpendicular is going to be a continuing theme in this course, so make sure you understand how to do that. Okay, so this is the coordinates we're going to want to work with. What are our forces on here? Well, we're going to have a normal force that's going to be pointing directly out of the surface. We are going to have the force of gravity that's going to be pulling down on the skier. It's going to be mg. And we're going to have the force of kinetic friction in this direction. Why? Because, well, the skier is going to be skiing downhill, right? Slides down the hill, and the force of kinetic friction is always going to oppose motion, right? So Fk has to be pointing uphill right here, okay? And we're told the magnitude of this kinetic friction is 45 newtons. Okay, so what do we need here? Well, we want to find mu sub k, but we know that F sub k is equal to mu sub k times the normal force. So we can use this equation and just rearrange it. We want to find mu sub k. Well, that's just going to be equal to F sub k over the normal force, right? And we already know what F sub k is. That's just 45 newtons, and that's going to be over the normal force. Okay, so we already have this. Really, all we need to do is find the normal force. And that's not going to be very hard for us to do, because we have our diagram over here, and we already know how to break up the force of gravity into its two components. We talked about this a few videos ago, right? But I guess we can start off. Let's draw our free body diagram, and we'll go from there. So let's imagine free body diagram. I'm again going to try to preserve the directions here. So we're going to have the force of kinetic friction pointing in this way. We have the normal force pointing in that way. But now we're going to split up our force of gravity into its two components. So we're going to have some part, and I'm going to call this whatever, we can call it Fg here, let's say. So we're going to have some part of Fg pointing parallel and some part of Fg pointing perpendicular. Okay? And so we are interested in what's happening in the perpendicular direction, right? We're interested in the normal force, and so we're interested in what's going on in the perpendicular direction. In other problems, we might be interested in what's happening in the parallel direction, but for now it's not going to matter very much. But let's remember that we know how to break this up, and I'm not going to go into all the detail on this because we have it in the previous videos. But we know how to break up this force of gravity into force of gravity perpendicular. Well, that's just going to be the force of gravity times cos theta, right? And if you look back at those other videos, you can remember that we have this argument here that this angle in here is also going to be theta and so forth. But we go over that in the previous video. So as I said, we're not going to do it again here. And then we also know that Fg parallel is going to be Fg sine theta. And I wrote it down here just for the completeness, but we're not really going to need that. What we need is this equation here. Okay, and why do we need that? Well, Newton's second law is going to give us everything that we need here once we have that expression. So let's take a look at what's going on here. Okay, so Newton's second law tells us that the net force in the perpendicular direction has to be equal to mass times the acceleration in the perpendicular direction. Well, in the perpendicular direction, there is no acceleration, right? So the skier is not lifting off of the mountain, nor is the skier digging into the mountain. And so this is equal to 0, but the net force in the perpendicular direction is also equal to the normal force in the positive direction minus the force of gravity in the perpendicular direction. And that perpendicular is too large. There we go. But since this is equal to 0, this means that our normal force is equal to the force of gravity in the perpendicular direction. And if we substitute in what we have up here in the star equation, then this means that the normal force is simply equal to Fg cos theta, but we know that Fg is just mg, right? So this is just mass times our gravitational acceleration and also times cos theta. So what do we have? We have n equals mg cos theta, and from the equation that we had above, we know what mu k, our coefficient of kinetic friction, is going to be if we know what the normal force is. So we now know that mu k is going to be equal to 45 over mg cos theta, and we can substitute in numbers for that, so that's going to be 45 over, it was 62 kilograms, 9.8 meters per second squared, and the cosine of 25 degrees. If you entered in those numbers, and am I at the bottom of the page here? I'm not. So if you entered in those numbers, you would find that mu k is equal to 0.082. And again, these mu's are coefficients of friction, either kinetic or static. They have no units, so that's our answer. Okay? And that's pretty much all we're going to do in this video. In the next video, we're going to take a look at some more examples of this use of friction, some more complicated stuff, and we're going to move on to other stuff.